Hi, my name is Sanchu Tenjike, and I'm presenting my work on the evaluation and design of a continuous fluid desalination system. So basically, water that's not properly treated usually contains pathogen. In fact, 3 in 10 people lack access to safely managed drinking water services. But our planet is covered with water in our oceans and sea. This water usually contains salt, so that means desalination has the potential to address the issue of lack of water for everybody. I specifically work on the free desalination system. So the way it operates is, well, you freeze water, remove salt from the surface of the ice that's formed from that water, and after you melt the water. So the key component, the key aspect that really that the free desalination depends on is the segregation coefficient, which is the amount of salt in the ice as compared to the amount of salt in the running water as you freeze a certain quantity of water. So the lower this segregation coefficient, the more efficient the phase desalination is. So in terms of number of cycle. So if you want to go from 3.5% salinity, which is the average salinity of water from our ocean, to drinking standard anything lower than 0.05%, assuming a segregation coefficient of 0.2, will require 3 cycles. So I studied the freezing reservoir because there's a lot of things going on. So when you put water, you freeze it. As the ice is formed, there will be ejection of salt, which will make the water in the reservoir getting more and more and more saline. So as the salinity increases, the freezing point drops. So it can drop even to a point where the system doesn't freeze the water anymore. So we need to maintain a steady state. So that means we need to reject some water as we put water and extract it in the form of ice. So by doing so, we will maintain a steady state of salinity in the reservoir. So in order to do that, I've used a lot of conservation of mass of the water, as well as the conservation of mass of the quantity of salt in the entire system. So using those equations and the segregation coefficient as well, I was able to get an equation that looks like this, and that relates the number of cycles to the mass flow rate drop. So using those, assuming that we go through 3 cycles, the mass flow rate drop for 1 cycle will be 0.2. So now if you want to really obtain a drinking standard water and going through 3 cycles, the mass flow rate drop from initial to final will be 1%. This is pretty low, but we can address this issue by building a desalination system that has multiple cycles and that works together. I also work on evaluating the energy consumption of the refrigeration cycle of our system. So in order to do so, I needed to find the temperature in the evaporator as well as the temperature in the condenser. So the temperature of the evaporator, I assume that this temperature will be equal to that of the freezing reservoir. Therefore, we will only require to remove the latent heat of fusion. As the same thing this way, the temperature of the condenser will be the same as the freezing point of the ice. So with that being said, I studied the freezing point of salt of water at different salinity level. Using this data, I was able to obtain a graph that gave me the freezing point in the freezing reservoir, as well as the freezing point in the of the ice form. So that will be the freezing point of the evaporator, and this will be that of the condenser. Using those, I was able to obtain a counter coefficient of performance of 150, but this assumes that you have a perfect system, no heat loss, temperature, only heat, latent heat is being transferred, and this gives us an energy consumption of 6.16 and 10 to the minus 4 kilowatt hour per kilogram. This is lower than the energy consumption per kilogram of that of multi-stage flash distillation as well as reverse osmosis. So that means this approach has the potential to contribute to the sustainability of our planet with lower energy consumption, but it requires us to look further to explore and study the system in more in depth. So for us to do that, we need to produce a detailed CAD drawing of a prototype and identify the most efficient freezing approach, as well as study the scraping mechanism and explore a multi-cycle system. I want to take this opportunity to thank Dr. Brian Hellenbull for being my mentor throughout this journey, as well as the honors program for all the help I have received. Thank you very much for watching, and I hope you enjoyed.